This is fundamental problem 5 from chapter 18. If the uniform 30 kilogram slender rod starts from rest at the position shown, determine its angular velocity after it has rotated 4 revolutions. The forces remain perpendicular to the rod. So I have my work energy conservation law. This is equation 1818. And I need to figure out what the initial kinetic energy is. Well, the rod is starting from rest, so T1 is equal to 0. And I need to figure out what the change in gravitational potential energy is. Now, in this problem, because the mass center is not at point O, the mass center is somewhere over here, the height is actually changing as the rod rotates. But when you go through one full revolution, the mass center ends up right where it started at. So if you go through 4 full revolutions, the rod is ending at the exact same position that it started from. And so the change in gravitational potential energy is 0, since the change in height of the mass center is 0. Okay, and then let's skip the work for now and find the final kinetic energy. So from equation 18.6, the final kinetic energy is 1/2 mvg squared, where vg is the velocity of the mass center. And then I have 1/2 ig times omega squared. Well, actually, instead of using this equation here, since I have a fixed point O, I could use equation 18.7. So I can say T2 is equal to 1/2. And remember, we can use this equation for the instantaneous center or for a fixed point O. Then if I use this equation here, I just need to find the moment of inertia about point O. Well, that I can do using the parallel axis theorem here, which has my new moment of inertia, I, is equal to the moment of inertia about the mass center plus the mass times the distance squared between the mass center and your new point. So if my new point is point O, this is mass times the distance squared between those 2 points. So if you look at our rod, we have 0.5 here, 0.5 here, 1.5 here, and 0.5 here. So the total length of the rod is 3 meters. The mass center is right in the middle, so that would be 1.5 meters from either end, which means that the distance between the mass center and point O is 0.5. So then, to find the moment of inertia about point O, we just go to the back of the textbook and figure out what the moment of inertia is about the mass center for the slender rod. That would be either the x-axis or the y-axis. That's 1/12 times the mass times the length of the rod squared. So this is equal to 1/12 times the mass. The length of the rod was 3 plus the mass times 0.5 squared. And then if you do 3 squared, you get 9. 9 divided by 12 is 3/4. 0.5 is 1/2. 1/2 squared is 1/4. So this is 3/4 plus 1/4, which is just 1. That is that would be 1 meter squared times the mass, which was in both terms. So that's the mass times 1 meter squared, but since we're leaving out the units, that's just m. And then the moment of inertia would have units of kilograms times meters squared. Okay, now I needed the moment of inertia in order to find the kinetic energy in event 2. So T2 is equal to 1/2 times the mass times omega squared. But remember that the units are different there because that's for the moment of inertia. Okay, so then I also have to find the work done by forces other than gravity. So that would be my 30 Newton force here and my 20 Newton force here. For the work done, you have, well, this is also the sum. So this is going to be the work done by both forces. For each force, and never mind, let's just do for one force. So this is equation 18.8. So for one force, you would have the force dotted with the displacement. And for this force, this point is moving in the same direction as the force because the rod is rotating this way. At this point is moving in the same direction as this force. So for either one of those forces, when you do the dot product, you would just get FDR. Both of these forces are constant, so you can pull the force outside. And then you can do this and you'd get delta R or delta S. Then using the arc length formula, so let's say F times delta S, where this is the distance that this point travels through or the distance that this point travels through. Using the arc length formula, delta S is equal to R times delta theta. So the distance that this point travels through would be 0.5 times delta theta. The distance that this point travels through would be 1.5 times delta theta. So let's say for either one of those, we could call it F times R, where R is the distance from point O to the force, times delta theta. Then I have to do the sum of the work done. So for each force, the work done is positive. I have the 30 Newton force, so that's 30 times this distance here, which is 0.5, times delta theta, plus for this force, it's 20 newtons, times this distance, which is 1.5, times delta theta. So delta S is not the same for both those points. Since this one is closer to point O, it travels through less distance than this point here, but delta theta is the same for both of those points. Okay, so now that I have all that, I can go back to my work energy conservation law, and I can put everything in. T1 is equal to 0. Delta V1 is equal to 0. My work is 30 times 0.5. Should be plus. That's 15. It's times delta theta times 20 times 1 plus 20 times 1.5, which is 30. So that's 30 times delta theta. That's equal to my final kinetic energy. My final kinetic energy that was here, that's 1/2 times the mass. Was I told what the mass was? Yes, the mass is 30 times omega squared. Oh, I even know what delta theta is because they told me 4 revolutions. So for 4 revolutions, delta theta is equal to 4 times 2 pi. So you can go ahead and plug everything in. We have 15 plus 30. Oh, wait. I missed this. So in the problem here, we have a 20 Newton meter couple moment. And so I also have to find the work done by the couple moment. Okay, so this was the sum of the work done by the two forces. Then for the couple moment, we use the equation here. It's constant at 20. So we can pull that outside and then we just get 20 times delta theta. So it's this plus this, and then for the couple moment, we have plus 20 times delta theta. And so then we have in here, we have a plus 20. So that would be 15 plus 30 plus 20, that's 65 times delta theta. Delta theta is 4 times 2 pi, and that equals 15 times omega squared. Therefore, you can solve for omega, and you should get 10.44 radians per second. And that concludes fundamental problem 5.